We're going to get into the meat and details of chapter 18. Yes?
Should that be a resonance arrow?
Right here? Yes, it should be. We're going to be talking about tautomers a little bit later today, so I'm in tautomer mode. But you're right, that's a resonance arrow. So at the end of class on Monday, we talked about hydrogens adjacent to carbonyls. In general, what we're going to learn today is true for any hydrogen adjacent to any electron withdrawing group. So we're going to focus on carbonyls, as the book does for chapter 18 and 19, 18 and 19. But I can't stress enough that any electron withdrawing group, like nitro groups or nitriles, are going to behave very similarly. So if you have a hydrogen on a carbon adjacent to an electron withdrawing group, it's going to be surprisingly acidic. And I'll be talking about this later on in the chapter, but if you want to prove it to yourself, draw a hydrogen adjacent to a nitro group, deprotonate that hydrogen, and ask yourself, is this anion resonance stabilized? And you'll see it is. And so the most basic reason why these hydrogens have low pKa's in the 20s, low 20s, is because when the base takes the proton, the resultant anion you have, we say can resonate into the carbonyl. So this is just like any lone pair of electrons adjacent to electron withdrawing group, so it can resonate into the carbonyl, giving us a resonance structure. We're now, instead of having a minus charge under carbon, we now have a minus charge under electronegative oxygen. So you can imagine this is a very huge contributor, resonance contributor to the resonance hybrid. And in fact, this is the way chemists really think of enolates. It's with an oxygen with a minus charge, and then this very electron-rich double bond. That being said, the reactivity of enolates is more similar to this resonance structure where we have a minus charge at carbon. So 90% of the time, if you throw in an electrophile in the presence of one of these enolates, the electrophile is going to react at the carbon. So an enolate is nucleophilic at the carbon. And that's pretty much going to be the basis of the next two chapters. So first off, I want to look at this deprotonation event in a little bit more detail to bring up some really important facts about hydrogens adjacent or alpha. So whenever we have a carbon that's adjacent to an electron withdrawing group, we call it alpha carbons, alpha adjacent. That's not why we call them alpha carbons, but it's a good mnemonic device. So they're adjacent or alpha to an electron withdrawing group, the carbon is. And then the substituents off of those carbons, i.e. the hydrogens, we still refer to as alpha hydrogens because they're on the alpha carbon. So alpha hydrogens are acidic. And the real reason why, the rigorous way to think of this is, if you draw this in 3 dimensions, you can rotate this bond so that the lone pair of electrons in the carbon are overlapping with the pi star orbital. And so then when you have orbitals overlapping, you can have resonance and great stabilization. So what's the hybridization of this carbon? sp2. This is an sp2 carbon, just like the nitrogen with the lone pair of electrons adjacent to a carbonyl is an sp2 nitrogen. So the key stabilization, or what's really key for stabilization, is that the resultant anions, the lone pair of electrons in the carbon, has to overlap with the the pi star, so the antibonding pi star orbital. If we do not have overlap, even if you're alpha to a carbonyl, if you can't get this overlap, then it's not going to be stabilized. I'll show you an example in a second. By extrapolation, so we know the lone pair of electrons has to be overlapping to be stabilized. What that means is the hydrogen, for it to actually be acidic, the sigma bond of the hydrogen has to be able to overlap with the pi star. So in and out of the board, I'll draw our pi star orbital for the carbonyl. So our carbon, oxygen, pi star. So in order for a proton to actually be acidic, the electron, you have to be able to rotate the bond so that the hydrogen you're deprotonating is able to get a good amount of overlap with the pi star. And so really what the deprotonation really looks like, so in black I drew it to get this resonance structure where the base takes the proton and the electrons go on the carbon. In reality it looks more like, and I'll do this in orange, is the base takes the proton and then the electrons from the carbon-hydrogen bond actually go into the carbonyl and then the electrons go into the oxygen. So the orange arrows are probably more realistic to what happens. But yes.
So they're just different resonance forms?
Exactly. And both are valid, but just kind of like what, I guess the more, they're both correct, but the more realistic thing of what actually happens is the orange arrows where the electrons from the deprotonated hydrogen now go into the anti-bonding orbital of the carbonyl, causing the pi system of the carbonyl to become a single bond. And so how this really manifests itself is if you have a cyclic rigidified system. All right, so in a case like this, a single bond in the starting material, we are free rotation. So it's not going to be very hard at all to rotate this bond so any of the hydrogens can overlap the pi star. Right, single bonds have free rotation, so that's going to be fairly trivial. So you guys agree with that? So now let's take a rigidified system. And I'll draw the hydrogens, one in blue, one carbon's hydrogens will be blue. And I'll draw the other hydrogen in red. And let me try the pi star orbitals. So first off, this molecule, I can probably ask, it would be fair for me to ask you guys how to make this molecule, because it's all chemistry that you have already learned in 232 and 432 to make something. Does anyone want to throw out just a real brief proposal of how to make a molecule like this? Alright, Diels-Albert, first step. What would the next step be? So that gives you an olefin. What do you do to the olefin? Well, you want to go from an olefin to a carbonyl. So maybe you do some kind of acid catalyzed hydration followed by an oxidation. So, you know, this looks like a more complex molecule than it is, but from what we know, we can make it. So anyway, this is a bicyclic system, and which means it's very rigid. So, whereas these bonds have free rotation, so it's not that hard to get overlap for any of the hydrogens, a system like this is now very rigid. It's a bicyclic system, it's not going to be able to rotate very much. And so pretty much the atoms are where they are. The atoms aren't going to be able to move, the bonds aren't going to be able to rotate. So what that means in this case, only one of the alpha carbon's hydrogens are actually acidic, whereas the other alpha carbon's hydrogens are not acidic at all. So they're more like methane than a typical alpha carbonyl. So which hydrogens do you think are going to be acidic, blue or red? Blue or red? I heard one person say blue, one person say red. So overall, who thinks it's going to be the blue protons that are acidic? Who thinks it's going to be the red? All right, it looks maybe blue slightly winning. So let me think of it this way. So I drew the pi star orbital in green. It's not the best pi star orbital, but gives you a rough representation of where the anti-bonding orbital is. The hydrogen here, if you look, it actually bisects the pi star orbital. So let me put this another way. This hydrogen is in the same plane as the carbonyl bond. And pi star orbitals are actually bisecting the carbonyl bond. And so if the pi star orbital is bisecting this carbonyl bond, and this hydrogen is in the same plane as this carbonyl, that means that this hydrogen is also bisected by this. So what that means is, in this case, this hydrogen is perpendicular to the pi star orbital. So knowing that the hydrogen is perpendicular to the pi star orbital, would you expect that hydrogen to be acidic or not acidic? Not acidic. So this hydrogen has almost no overlap. It pretty much, since it's parallel to the carbonyl, it is perpendicular to the pi star orbital, thus there's no overlap. And so if you were to make, in theory, the resulting cation, there would be no way for it to resonate into the carbonyl because there would be no electron overlap. So that this hydrogen, this is perpendicular to the pi star orbital, so no orbital overlap, no resonance. So surprisingly, this hydrogen behaves a lot like a typical methane hydrogen. It's not very acidic at all because there's no orbital overlap to stabilize it. Conversely, in blue, the hydrogens, where they don't have perfect overlap, they have pretty good overlap. So that if you were to make a anion, like so, by throwing in a base, now the lone pair of electrons are indeed kind of overlapping with the pi star, so they can resonate to give us our enolate. So what I'm only trying to show here is, and this is something I wish I would have appreciated before I went to graduate school, because this would have made things a lot easier for me in my upper division chemistry classes here, as well as my first year graduate classes at Yale. But I really didn't appreciate this fact until I was, maybe 6 months in to graduate school. But it's this electron overlap of the hydrogen with the pi star orbital is crucial, and if you don't have that orbital overlap in a rigidified system like this, your hydrogen is not going to be acidic. Yes?
Why does that produce more acidity?
Because acidity is just how stabilized is your conjugate base. And so in that case, your conjugate base, as drawn here with this lone pair of electrons, can resonate into the pi star orbital. Whereas in this case, since this bond is perpendicular, when we make the resultant anion, it cannot resonate. So it's just, in order to resonate, you need orbital overlap. And so one case has orbital overlap, so it can get resonance stabilization, and that's blue. But however, in red, you do not have overlap, so you cannot get resonance stabilization. So that's the basic of forming enolates. And again, enolates are nucleophilic at carbon. Before I get into the chemistry, I want to talk about another enolate-like thing called enol. And an enol is a tautomer of a carbonyl. So here's acetone, here's a typical ketone. And in this case, I'm drawing equilibrium arrows, not resonance arrows. So all carbonyls have the possibility to exist as a tautomer. Between the carbonyl form and then what we call the enol form. And so just to think of it just very basically, this equilibrium, let me actually make the arrows more realistic. This equilibrium pretty much can occur by the hydrogen jumping from this carbon to the oxygen and having this electron flow to give us the enol. So think of it as the carbonyl taking this hydrogen almost as if it's a base. And this is really just mnemonic. I'll show you the real mechanism for this in a second. But in neutral conditions, which this doesn't happen under neutral conditions, even though in theory could, it would be the oxygen taking this hydrogen as a base, causing these electron densities to kick into this bond, causing this to go up. So it's very similar to a basic deprotonation to give us an enolate. It's just an intramolecular thing that gives us our neutral enol. So when it comes to tautomerization, we call the carbonyl the ketotautomer. And we call the alcohol the enol. So the reactivity of enol tautomers are similar to enolates, just not as nucleophilic. So if you form an enol and you throw in an electrophile, it will react at carbon. And I'll show you some examples of that in a second. I just want to kind of start off the take-home message now is enols do react like enolates. Just as you can expect, since they're neutral, they're a little bit less reactive than anionic enolates. So they're a little bit less nucleophilic. But they can still react. So any carbonyl can exist between this keto and enol tautomerization. So which tautomer do you think is favored under neutral conditions? The keto form, right? Because we always talk about ketones and aldehydes, not enols and enols. Right, so obviously that should kind of give us an idea that, okay, the carbonyls are favored form. And that is very true. So in acetone, neutral conditions, and the chemistry majors here who take Chem 417 lab will actually be measuring this directly by NMR in a few years. So those chemistry majors who have this to look forward to, actually picking up this number. But in this case, at neutral conditions, we'll have at any time roughly 99.9% of the keto form. And 0.1% of an enol form. At neutral conditions. At neutral conditions. So, in general though, what we have found over the years is that the more acidic your proton is, the more the equilibrium lies towards the enol. So in black, I'm just writing the pKa of acetone. What do you guys think it is roughly? So 20 to 24 is a typical enolate pKa. So that's just a number to remember. A typical typical alpha hydrogen is a pKa of 20 to 24. That's the magic number for alpha hydrogens adjacent to electron withdrawing groups, 20 to 24, and acetone is 20. So 20 equals pKa. So a pKa of 20 gives you 99.9 to 0.1, favoring the keto tautomer. Whereas if you have an alpha hydrogen that's alpha to two different carbonyls, is this going to be more or less acidic than acetone? More acidic. Compared to zero, does anyone want to give me a rough ratio? Like how much more acidic? 5 orders of magnitude, 10 more orders of magnitude, 15 orders of magnitude? 10, exactly. It's when you have two hydrogens, it pretty much gives you an increase from 20 to 10. So now pKa equals roughly 10. So much more acidic. And so what actually the way that kind of transpires itself is that now when you're that much more acidic, So this is just the enol form of this dicarbonyl. Now the equilibrium favors the enol form. So for the more acidic proton, we go from 99.9 to 0.1, favoring the keto form. So now we are at 24% being the keto form, and 76%, so roughly 3 to 1 favoring now the enol form. So more acidic protons. The more acidic your alpha proton, the more enol tautomer you will have. And that directly correlates with the pKa of the alpha hydrogen. So the other thing about enols is you can bias. So for a thing like acetone has a low that favors the keto almost entirely, you can influence the equilibrium under acidic conditions. So under H3O and alcohol solvent, for instance, you can actually form entirely your enol. So your enol. So if you want to form an enol, what you do is you take your carbonyl. I'll do it in acetone. You take H3O plus, and you do it in some kind of protic polar solvent. I think I can normally do something like THF or some. You can even just do this in pure water, really. I wouldn't do this in methanol, because in methanol, what happens if you take carbonyl and throw it in methanol and acid? You get the acetal, right? So that's going to cause some issues. But you take acid and something like THF, you will get your enol out. And so the mechanism of this is not too crazy. First step is just a protonation of the carbonyl, so we've seen this as a common first step. And of course, that'll give us water out. And so now, with this protonated carbonyl, is this alpha hydrogen going to be more acidic than it was before? Absolutely, right now it's cationic and we really want to quench this positive charge. So now, once we protonate the carbonyl, now even though it now water is a strong enough base to deprotonate this hydrogen when this is protonated. And it gives us an enolate almost instantaneously, so an enol almost instantaneously. So by adding acid, you can drastically influence this equilibrium. So under acidic conditions, we now favor the enol. And perhaps just to tie in with this analysis saying, keto-enol tautomerization ties in with the pKa of the alpha hydrogen. When the carbonyl is protonated, this is going to be an incredibly low pKa of the hydrogen, so that just falls in line with, what we talked about earlier. So under acidic conditions, you can form the enol. And just up in this corner, I'm just going to remind you a typical way of how we form an enolate. So we form an enolate just by taking a base. The common bases we're going to be talking about in this class are sodium ethoxide, so the conjugate base of ethanol, and something called lithium diisopropyl amide. But just think about it, it's basically the conjugate base of an amine. The conjugate base of an amine. So N minus R2. And that gives us our enolate. So the reason I drew this is because I just want you to realize there's two different ways to form reactive enol or enolates. And a lot of the chemistry that I'm going to be showing you can be done either under acidic conditions or under basic conditions. Under acidic conditions, you go through the enol. Under basic conditions, you go through the enolate. But enolates and enols still are going to be nucleophilic at the carbon. And so the chemistry doesn't really change. It's just one's an anionic enolate and the other's a neutral enol. But they'll both react nucleophilically at the carbon towards electrons. And so I'm going to try to show you the acid and base catalyzed versions. What I might do is I might show you one of the mechanisms, and then say the other mechanism is via the enolate or enol, but it's very similar furthermore. But really, they're interchangeably. Although, in my experience, I do a lot more enolate chemistry, or have done a lot more enolate chemistry, than I have done enol chemistry. So you can take that for what it's worth. Maybe I'm just a very basic guy. So, let's get into the chemistry of enolates now. Enols and enolates. The first off, and this is more of a cautionary tale than anything, is if you have a alpha hydrogen that's on a chiral center. So just let me draw a chiral alpha hydrogen. Oh, that's not chiral, that's two methyl groups. Here we go. So this is a chiral alpha hydrogen. Esters versus ketones. One of these is slightly more acidic than the other. And by slightly, I mean 2 or 3 pKa units. What do you think is going to be more acidic? Ketone or a ester? And just let me tell you, this really goes in line with reactivities of carbonyls towards nucleophiles. It's the same reason for these two very different trends. So what do you think is going to be more acidic, an ester or a ketone?
Ester.
It's going to be a ketone.
Why?
Well, because with an ester, the lone-pair of electrons can donate into the pi star orbital, which is what we expect our minus charge in the carbon to do. So with esters, for that low energy anti-binding orbital, there's competition from the oxygen. Whereas with ketones, there's no competition for that lone pair going into the pi star orbital.
Okay, I was thinking about it.
All right. You're taking the inductive effect, right?
Yes.
Yeah. That's a classic thing that say, talk about the inductive effect and ask them the question and say, oh, actually, no, it's this. But I didn't want to be mean. But yes, no. So because esters can add electron density into the pi star orbital, the pi star orbital is going to be a slightly higher in energy. And what that means is we get a slightly less stabilization when we deprotonate the alpha hydrogen. But it's slight. We're talking, instead of having a pKa of 20, we now have a pKa of 23. Albeit, that being said, that's 1,000-fold difference. So I feel weird saying slight and 1,000-fold in the same sentence. But just beware, esters are slightly less acidic than ketones, but they're still acidic. So, when we have a chiral center, and I'll just draw our pi star orbital. So just to show the analysis I was mentioning, an ester alone pair of electrons can resonate into the carbonyl. That's what esters do. And so when we form the enolate, there's now the energy, the pi star orbital isn't completely empty because it's got the ester electron density. And so when the minus charge in our carbon resonates to get the enolate, it's going to be slightly less stabilized than if the oxygen wasn't there. That's a subtlety. It's a subtlety, but it's something that's nice to appreciate. So when we have an alpha carbon and hydrogen adjacent to when we have a chiral alpha hydrogen, it turns out they're not that stereochemically stable under acidic or basic conditions. And so what I mean is, if you treat this to acid, we're going to get our enol. We're going to get our enol like this. And of course, this will be in equilibrium. And since this is an ester, even under acidic conditions, we'd still expect there to be a significant contribution of this carbonyl. But, so this will be going back and forth between the enol and the ketone, and the enol and the ester, and the enol and the ester, so on and so forth. But, what I want to point out here is when we're in the enol form, this is sp2. So we go from having a chiral sp3 center to having a sp2 center. So what does that mean? Well, that means we lost our stereochemistry. And then when we go back to the ketone form, there's going to be no reason it can't come from either face. So it can come from, as drawn here, the top face to give us our initial enantiomer, but it can also come from the other face to give us the enantiomeric compound. And so basically, what I'm trying to say is, when you treat a chiral alpha hydrogen to acid or base, you lose your stereochemistry. So you can take a perfectly nice chiral compound and then actually get out a mixture of enantiomers. So you start out with something that's 100% one enantiomer, and because you destroy your chirality when you form the sp2 at that carbon enol, when you reprotonate it, the product you get out lost that stereochemistry. So chemistry does not have a very good memory. So when we go from an sp3 chiral center to an sp2, we destroyed that chiral center, and then when we go back to the carbonyl through whatever